Hi, I'm Matt, and in this video we're going to talk about how to evaluate limits as x approaches positive or negative infinity, specifically for polynomial and radical functions. So first, let's talk generally about limits as x approaches infinity. So first, there are two types of limits at infinity we need to look at, and that's the limit as we approach positive infinity, which we denote in the notation by putting an infinity here. And then we also have the limit as x approaches negative infinity. So in that case, we would put a negative infinity as what we approach. So now for these two types of limits as x approaches infinity, so again, one positive, one negative, there's four possible things that it can do. First off, it can converge to a finite value. This is the case when we have a horizontal asymptote. We could also have it be infinity if the function increases without bound as we go towards infinity. We also could have it be negative infinity if the function decreases without bound. And then the last possible option is that we could find the limit as x goes to infinity or negative infinity doesn't exist at all. This is the case when the function never converges, and often what we see when this occurs is that we have an oscillatory function such as the sine function. The sine will always oscillate between negative 1 and 1 as we go towards infinity, so it would be impossible to say where it converges to at infinity. So now, when we have polynomial and radical functions, how do we determine the limit as x approaches infinity? So the first thing we're going to want to do is if our function we're looking at, f of x, isn't already a fraction, we're going to divide it by x to the 0, because x to the 0 is just 1. And the reason we want to add an x to the 0 in the denominator is eventually we're going to get to 3 separate cases, and it's just easier to write those rules when they're as a fraction. So once we have it put it over an x to the 0 if necessary, we're going to remove all terms in the numerator except for the term which is the largest exponent and its leading coefficient. This seems probably like a very big step to remove all other terms, but the reason for this is let's take the example of x to the 5 plus 1. If we have a very, very large number and we add 1 to it, the number really doesn't change. So x to the 5th plus 1 for very large x values is approximately just x to the 5th. Similarly, if we had x to the 5th plus x to the 4th, x to the 5th will increase or decrease a lot faster than x to the 4th because of the additional plus 1 in the power. Therefore, when we consider limits as x approaches infinity, its behavior is only going to be determined by that highest exponent. Now that we've done this in the numerator, step 3 is just to repeat step 2 for the denominator. So again, in the denominator, we'll remove everything except the term with the largest exponent and its coefficient. And lastly, we're going to simplify the function as much as possible from here. What that means is that we should have the function with all positive exponents. And once we have it with all positive exponents, it should be in the form ax to the n divided by bx to the m, where n and m are both greater than or equal to 0. And a and b should both be real numbers in this case. So now, again, just to reiterate, we have it in the form ax to the n divided by bx to the m. And now from here, we're going to look at 3 cases that we'll use to determine what the limit is. So if m is greater than n, if the exponent in the denominator is greater than the exponent in the numerator, regardless of the coefficients, the limit as x approaches infinity and the limit as x approaches negative infinity will be 0. And that's because the denominator will be increasing at a faster rate than the numerator. So for very large values, we're going to end up with a small number over a very large number, which is approximately 0. Next, if m equals n, we'll find that the limit as x approaches infinity will be a over b or negative a over b. And that we could just think of as the x to the n canceling with the x to the m, because they will cancel if n equals m. Similarly, as we go towards negative infinity, we could also have positive or negative a over b. And we'll discuss how we figure out the sign in a moment. Now the last case is if n is greater than m, so if the exponent of the numerator is greater than the exponent of the denominator. In this case, we're going to find that the limit as x approaches infinity is either positive or negative infinity. Similarly, the limit as x approaches negative infinity will also be infinity or negative infinity. This is because when we have a larger exponent in the numerator, we're going to see that the function is increasing at a more rapid rate in the numerator. So when we look at the numerator and the denominator, overall we'll see that the function will either be increasing without bound or decreasing without bound. To determine, for both the second and the third case, to determine if it's positive or negative, we're going to want to observe the numerator and the denominator and see if they would be positive or negative, and then use our typical negative rules, such as a negative over a negative is a positive, etc. And we'll look at how to do that when we look at some examples. So, for our first example, we want to find the limit as x approaches negative infinity and the limit as x approaches infinity of 1 divided by x squared. So, going through our steps, we're initially going to skip the first step because there's already something in the denominator, so there's no need to add a denominator. For the second step, we don't need to cut out any terms because we already are down to only one term in the numerator. Similarly, we don't need to cut out any terms in the denominator because, again, there's only one term. So we're going to start with step 4, which is trying to rewrite 1 over x squared in the form ax to the n divided by bx to the m. To do this most clearly, we're going to take our 1 over x squared and we're going to rewrite it as 1 times x to the 0 divided by 1 times x squared. So again, we're allowed to do this because x to the 0 is just 1. So really we just multiplied our numerator and denominator by 1, but again, it's now in the form that we can apply our rules. Since 0 is less than 2, we find that m is greater than n, or that our exponent in our denominator is greater than our exponent in the numerator. And since the exponent in the denominator is greater, we're going to find that the limit as x approaches infinity of, I'm just going to call 1 over x squared f of x, is equal to the limit as x approaches negative infinity of f of x, and that is going to be equal to 0. And again, that's because in this case, x squared is increasing at a much greater rate than just the constant 1. So we see that as we go towards negative infinity and infinity, our function will go to 0. For our second example, let's evaluate the limit as x approaches negative infinity and as x approaches positive infinity for the function f of x is equal to x cubed. So here we will have to do the first step because there's no denominator. So I'm going to rewrite x cubed as x cubed divided by x to the 0. And again, so we just divided it by 1 essentially. Step 2 and 3 we can skip because we only have one term in the numerator and one term in the denominator. So now we're up to step 4, which is where we need to write it in the form ax to the n divided by bx to the m. To do this, we really just need to multiply the numerator and the denominator by 1 again. And what we find finally is that we get 1 times x to the cube divided by 1 times x to the 0. And from here, we can now apply our rules. Since 3 is greater than 0, we find that n is greater than m. So based off that, we know that our limits as x approaches negative infinity and as x approaches positive infinity, we know that we're going to get infinity or negative infinity for those. But now we need to figure out which one. So we're going to start by the limit as x approaches negative infinity of x cubed. So the bottom's always going to be 1, so we don't need to consider the bottom in sign because it's going to be positive. But now let's look at the numerator. So as we go towards negative infinity, we're going to have a very large negative number. And when we cube it, we're going to end up with a negative number times a negative number times another negative number. A negative times a negative makes a positive, but then a positive times a negative makes another negative. So we find that we're going to get a very large negative number, meaning that the limit as x approaches negative infinity of x cubed is going to be equal to negative infinity. Now we're going to do the same type of analysis for the limit as x approaches positive infinity of x cubed. To do this, we're going to see that we're going to take a very large number, or a very large positive number specifically. And since it's x cubed, we'll have a positive number times a positive number times a positive number. And a positive times a positive will always give another positive. So we find that x cubed as we go towards infinity will be a positive number. Therefore, it will be positive infinity. Now for our final example, we're going to look at the limit as x approaches negative infinity and the limit as x approaches positive infinity of 2x cubed plus x divided by 3x squared minus 4x cubed. So we could start by skipping the first step because this function is already written as a fraction. And now I'm going to rewrite this function before we go to step 2. So what we find now is that we have two terms in the numerator and the denominator, and according to step 2 and 3, we only want to keep the largest one. So when we compare x cubed and x, the x to the 3 will have the largest exponent, so for the numerator, we're only going to keep the 2x cubed. So when we rewrite it, that's the only piece we're going to rewrite. Similarly, in the denominator, we have an x squared and an x cubed. 3 is greater than 2, so we're only going to take the second term. And be careful that when we take the second term, we include the negative. Lastly, before we go forward, we could simplify these coefficients a little. So I'm going to rewrite this as negative 1 times x cubed over 2 times x cubed. This won't always be the case, but just since 2 divided by negative 4 was simplifiable, it definitely will simplify computation later. So now we see that 3 equals 3 as our exponent in the numerator is equal to the exponent in the denominator. So n is equal to m. And when n is equal to m, we know that the limit will be the ratio of our numerator to our denominator. So in this case, we know that our limit as x approaches infinity and negative infinity is going to be equal to either plus 1/2 or minus 1/2. And now we're going to need to look at an analysis of our positives and negatives to see which one. So first, let's work with the limit as x approaches negative infinity. In the numerator, we have a negative coefficient because we have a negative 1 and then times x cubed. Since we're looking as we go towards negative infinity, x is going to be negative, so we end up with a negative from the coefficient times 3 negatives for our x cubed. Now for the denominator, we have a positive 2, so our coefficient is positive, and then x cubed will again be a negative times a negative times a negative. Therefore, we end up with 4 negatives in the numerator, which will make a positive, and then the product of 3 negatives and a positive in the denominator, which is a negative. A positive divided by a negative is a negative. Therefore, we find that as we go towards negative infinity, we're going to end up with negative numbers. Therefore, the limit as x approaches negative infinity of f of x is going to be equal to the negative result, or negative 1/2. Now let's look as the limit as x approaches positive infinity of f of x. So just as before, we still have a negative coefficient in the numerator and a positive coefficient in the denominator. However, as we go towards infinity, x cubed is going to be the product of 3 positive numbers. So in the numerator, it's going to be a negative times 3 positives, and in the denominator, it's going to be a positive times 3 positives. Therefore, we get a negative divided by a positive, which is just another negative. So, again, we're going to use the negative possibility for our limit, which says that the limit as we go towards positive infinity of f of x is also going to be negative 1/2. So, just in summary, our limit as we approach negative infinity and our limit as we approach positive infinity for this question will both give us negative 1/2. For our final example, we're going to now look at a question with radicals. So, since it's already a fraction, we don't need to divide it by x to the 0. However, the one thing we will want to do is, just as before, do step 2 and 3 and simplify our numerator and our denominator. So I'm going to start by writing 5x squared minus 2 divided by x plus 3. And then from here, I'm going to want to remove the term that doesn't have the highest exponent. So in the numerator, we have 5x squared, and then we have the constant negative 2. Since negative 2 could be thought of as negative 2x to the 0, we know that the 5x squared is going to win, so to speak, in that it has the largest exponent. So our numerator is just going to become square root 5x squared. And then in our denominator, we have an x and a 3. X is x to the first power, while 3 only has an x to the 0. So our x is the one that takes priority. So we end up with the square root of 5x squared divided by x. Next, I'm going to break up the numerator into the square root of 5 times the square root of x squared. And we could do that based on our rules of radicals. So now we have square root 5 times square root x squared divided by x. Now I'm going to make one more simplification here, and that's that we get square root of 5 times the absolute value of x divided by x. Typically, when we take the square root of x squared, we would just write that it's x. But I'm going to be very precise here and write that it's actually the absolute value of x, because any number squared will give us a positive under the radical. Therefore, when we end up with a square root of x squared, we precisely get absolute value of x. So now from here, even though we have an absolute value symbol in the numerator, we still can think of this as x to the first. Similarly, our denominator is x to the first. So we find that n equals m, so our limit as we go towards positive or negative infinity will be the positive or the negative ratio of coefficients. Imagining a 1 in the denominator, we see that our limit will be plus the square root of 5 or the negative square root of 5. And to figure out the signs, we're going to do the same thing we did in our previous example. So we're going to start with the limit as x approaches negative infinity. So for the limit as x approaches negative infinity, we're going to have a positive coefficient times x. If we're going toward times the absolute value of x. Since it's the absolute value of x, we know it's going to be positive regardless of where we're going. In the denominator, we have the positive 1, so a positive coefficient, times x to the first. Here, since we're going towards negative infinity, that x is going to be negative. So we end up with a positive times a positive, which gives us a positive in the numerator, divided by a negative in the denominator, which gives us a negative. Therefore, we're going to take the negative possibility for our limit, and we find that the limit as x approaches negative infinity of f of x is equal to negative square root 5. Now let's do the limit as x approaches positive infinity. The limit as x approaches positive infinity of f of x, to do that, we're again going to have a positive coefficient, and then the absolute value of x is always positive. Therefore, our numerator will still be positive. In our denominator, we now have the positive 1, or the positive coefficient, but now x to the first, x is going to be a very large positive number, so we still get a positive. This gives us a positive divided by a positive, which is just a positive. Since we get a positive, we know that the limit that x approaches infinity of f of x is going to be the positive value for our limit. Or it's the positive possibility, I should say. Therefore, we find that the limit as x approaches infinity of f of x is the positive square root of 5. Now, I know that this is a longer video, and those were 4 long examples, but here are still 4 practice problems for you to try on your own. The answers to these problems will appear in 5 seconds. Okay. So for the first example, you should have gotten that the exponent of the numerator was greater than the exponent of the denominator, and you should have gotten that the limit was negative infinity for both of them. For problem 2, you should have gotten 0 for both of them, as the exponent in the denominator is greater than the exponent in the numerator. For problem 3, you should have gotten positive 3 halves for both. Here that was n equaled m, and you needed to figure out the signs. And for the last problem, you should have gotten 1 divided by the square root of 6 as we went towards negative infinity, and negative 1 divided by square root of 6 as we went towards positive infinity. Okay, thank you so much for watching. If you have any questions, feel free to leave them in the comments below, and have a great day.